Good afternoon, guys. This is Mike coming back at you with yet another video on Foundations of Math 2. In the previous video, we talked about the addition rules for probability, and we used those to determine the probability of two events happening, specifically A or B. In this video, we are going to talk about multiplication rules of probability. And we're going to use them to figure out the probability of two events A and B happening. So this calculation that we do to find the probability of both events happening A and B, not A or B, the calculation can be easy or it can be slightly more complicated based on whether or not the events are independent is the key word there. Two events A and B are independent if the outcome of one has no impact on the outcome of the other. This is the same thing as saying mutually exclusive, that two-word phrase that we saw in our previous video. For our purposes, those two things, mutually exclusive as well as independent, those two things are saying the same thing. Just some quick samples of events that are independent. You take two separate fair coins and you toss them. The outcome of one is not going to have any impact whatsoever on the outcome of the flip of the second coin. So if your two events A and B are indeed independent, then the probability of A and B happening is simply the product of the probability that A happens and the probability that B happens. P of A and B is equal to P of A times P of B. So let's go through a couple sample problems here just to sort of show this formula being used. What's the probability of picking a black face card and a 7 from a regular 52 card deck? So obviously these events of picking a black face card and picking a 7, these are clearly independent events. We can't have both these things happening at the same time. The other assumption here is that we do take the card that we first pick and we put it back inside of the deck here, so there is replacement happening. But you can't pick a black face card and a 7 at the same time. The face cards are jacks, queens, and kings, not 7s. So the probability of picking a black face card and a 7, so P of black face card and 7 is equal to the probability of picking a black face card times the probability of picking a 7. All right, what's the probability of picking a black face card? Well, we said the face cards were jacks, queens, and kings. We have 2 suits, clubs, and spades. So there are 6 black face cards out of the possible 52 card deck. And what's the probability of picking a 7? Well, there are 4 7s in a deck of 52 playing cards. So we do 6 over 52 times 4 over 52. And we know that when we take products of fractions, we simply multiply the tops and we multiply the bottoms. If you do 52 times 52, you get 2,704. And I can divide each of these numbers by 8. So I can pull out that common factor of 8 and cancel it out. And that gives me 3 divided by 338. So that is the probability of picking a black face card and picking a 7. Note that although we didn't necessarily specify how many picks we are taking, the sort of assumption here, the sort of underlying feeling is that we're doing 2 picks and we don't replace these cards. So second problem here, you roll 2 fair dice. We're going to assume that they are 6-sided here. 2 fair 6-sided dice. What's the probability that both rolls are odd? This is another example where the outcomes of the first roll and the second roll are independent. What we get for the first roll has absolutely 0 impact on what we get for the second roll. So we can write this as the probability that roll 1 is odd and roll 2 is odd. Again, these events are not dependent upon each other in any way, shape, or form. So this is just going to be the probability that roll 1 is odd times the probability that roll 2 is odd. So we have each one of these die is a fair 6-sided die. Roll 1, okay, you have the numbers 1 through 6 on each of the 6 faces. The odd numbers are 1, 3, and 5, so 3 out of a possible 6 numbers. And roll 2, same thing, 6-sided die, numbered 1 through 6, 3 faces that have odd numbers on them out of the possible 6. And this is the same thing as 1/2 times 1/2, and 1/2 times 1/2 is 1/4. So the probability that both rolls are odd is going to be 1/4. So I want to go back to this question here. This first one here, the probability that we picked a black face card and a 7 from a regular 52 card deck. And we were working under the assumption that we do replace the card once we've picked it, and then we make our next pick. If we specified that we don't replace the card, then there would be an impact on the probability. It would not be 6 over 42 times 6 over 52 times 4 over 52. It would change things slightly. If the events are not independent, that is to say, the outcome of one event will have some type of impact on the outcome of the next event, then our formula changes slightly here. The probability of A and B happening in this case, when your events are not independent, is that P of A and B is equal to P of A times the probability of B given A happening. So A is your first event, if you will. That happens, and then you want to multiply that by the probability that B happens given the result of A. So here are some sample problems. You choose between 10 pre-made dishes. 4 of them have been undercooked. If you choose 2 dishes, what is the probability that both dishes chosen are indeed undercooked? And we're specifying that you don't replace the dish once you've chosen it. You take it and that goes home with you. So this is a sample, or this is a case where the events, if you want to label them A, first dish chosen is undercooked, and then B is second dish chosen is undercooked. These, or this is a case where the events A and B are dependent. The outcome of A will have an impact on the outcome of B. Or to be more clear, the outcome of A will have an impact on the probability of B happening. Sorry. So, P of A and B is going to equal, as we know, P of A times P of B given A happening. All right, so what's P of A here? P of A is the first dish being chosen that is being undercooked. So what's the probability that the first dish we choose is indeed undercooked? Well, there are 10 dishes, 4 of them are undercooked. So you have 4 chances to pick something that's undercooked out of a possible 10. So I have 4 over 10 as the probability of A. Now, the probability of B happening given that A happened. What's the probability that the second dish we choose is undercooked given that we've already chosen a dish that is undercooked? Well, after picking one dish that was undercooked, there are now 9 pre-made dishes left, and now there are 3 dishes that are undercooked. So making the note here, after A, 9 dishes left, 3 undercooked. So now what's the probability of B happening given that A happened? Well, there are 3 dishes that are undercooked, and there are 9 possible dishes left to choose from. So the probability that B happens given that A happened is going to be 3 over 9, or 1 over 3. 4 over 10 reduces to 2 over 5. 3 over 9, as we just said, reduces to 1 over 3. So 2/5 times 1/3 is going to equal 2/15. So that's the probability that we choose 2 dishes that are undercooked when, to start with, we had 10 pre-made dishes and 4 of them were undercooked. So it's because we didn't replace that first dish, that's what changes this guy here just a little bit. That's what makes us say, okay, these events are dependent, because based on what we choose for the first one, based on what the outcome of A is, that does have an impact on what B is. If I can go back to the first question here, back to our sample of probability of picking a black face card and a 7, we said that this was with replacement. If it was without, then the probability, yes, our first pick, if you will, probability of picking a black face card would be 6/52. And then if I don't replace that card, there's now 51 cards left. What's the probability of picking a 7? Well, there's still the 4 7s left, and that's out of a possible 51 cards left. So this is equal to 24, because again, we're just multiplying the tops. And 52 times 51, if you plug that into your calculator, you get 2,652. And if you simplify that at least a little bit more, you come up with 12 over 2,652 divided by 2 is equal to 1,326. And this is equal to 6 over 663. So a little bit different of a probability here. If you do 6 over 663, you get approximately 0.009. If you do the probability calculation that we did first time through, if you do 3 over 338, you get approximately 0.00888. So slightly smaller probability. So with replacement versus without it does have an impact on the probability of these kinds of things happening. So it will specify in the question which thing or which situation you have happening. It will say, the cards do get replaced or the cards do not get replaced. But that's just there to show you, how things can be impacted. This sample problem here, this just shows you that we can use this same kind of thing, sort of, but with three trials or 3 separate events happening. We have another regular 52 card deck. We pick 3 cards from this deck without replacement. What's the probability that you pick 3 aces? Okay, so you have, first up, first pick, the probability of getting an ace on your first pick. There are 4 aces. There are 52 cards left total. Okay, you've picked that ace out. We don't put it back because it's without replacement. You're now on your second draw. What's the probability of picking an ace on the second draw, given that you picked an ace on your first draw? Basically, given the new circumstances of how many aces are left and how many total cards are left in the deck, what's a probability that you pick an ace on your second draw? Okay, we have 3 aces left now. and there are 51 cards left in the deck. Because we took that first ace out, we didn't put it back. So the probability that we pick an ace on the second draw is 3 times 51. And now probability that we pick an ace on the third draw. Okay, there are 2 aces left now, and there are 50 cards in total left. So it's going to be 4 over 52 times 3 over 51 times 2 over 50. We can simplify each of these fractions. 4 over 52 is 1 over 13. 3 over 51 is 1 over 17. And 2 over 50 is 1 over 25. And if we do 13 times 17 times 25, we get 5,525. So that's the probability that we pick 3 aces here. 1 over 5,525, which, if you write that as a decimal, that is approximately 0.00018. Or 0.018%. So very, very small chances of that happening. But it is possible. So those were some sample problems with using this formula right here. P of A and B equals P of A times P of B happening given that A happened. Well, there's a special term for that P of B happening given A happening. It has its own name. It's referred to as the conditional probability of B given A. We specially denote it by P of B and then a vertical bar and then A. And its calculation is given by this formula right here. P of B given A is equal to P of A and B divided by P of A. This is also equal to P of A and B. There's the cap symbol that we use to stand for the and, like we saw all the way back in our chapter on sets, all divided by P of A. So let's go on and let's solve a couple sample problems, seeing how we calculate the conditional probability. Using the table that is given below, find the probability that a crime was motivated by religion, given that it was a crime against society. So we have the various motives across the top, crimes against persons, against property, and against society, and then the motivation, race, religion, sexual orientation. And then we have the totals for each of these columns and each of these rows. Note that the total number of crimes here is 5,351. So underlining the key pieces of my question here, find the probability a crime was motivated by religion, given that it was a crime against society. If we compare that sentence there to P of B given A, we see that the event B is going to be that the crime was motivated by religion, and the crime against society, or the fact that the crime was against society, is going to be our event A. It's P of B given A. So, in figuring out this probability, P of B given A is P of A and B divided by P of A, which, putting it back into words here, P of A and B is saying that it was a crime against society and crime was motivated by religion. That long thing divided by the probability of A, the probability that it was a crime against society. Crime against society there. So now let's use our table here and come up with these individual probabilities. So what's the probability that we had a crime against society and it was motivated by religion? Okay, well, we have the column for crimes against society. We have the row for crimes motivated by religion. So since we want the and, we have to find the entry that lies in both the column for society and the row containing religion. And that entry is your 12 right there. So the probability of the crime being against society and motivated by religion is going to be 12 divided by the total number of crimes, which we said was 5,351. And these are still theoretical probabilities that we are calculating here. So it's number of outcomes in the event divided by number of outcomes in the entire sample space. In this case, 5,351 crimes or outcomes here in the sample space. And then what's the probability that the crime was against society? Well, we're looking just for the total number of crimes that were against society. So the total number of crimes against society was 44, and that's out of 5,351. Okay, so we're taking the quotient of two fractions. Let's simplify that just a little bit. We know, going back earlier on in our course, that dividing by a fraction is the same thing as multiplying by its reciprocal. So this guy divided by this guy is the same thing as 12 over 5,351 times the reciprocal of that fraction there, times 5,351 divided by 44. The 5,351s cancel out, and we have 12 over 44, which is the same thing as 3 over 11. So the probability that a crime was motivated by religion, given that it was a crime against society, is going to be 3 over 11. Okay, let's switch the orders of these events A and B. Let's find the probability. I'll write it down here. Let's find the probability that it was a crime against society, given that the crime was motivated by religion. let's see how that changes. Let's see how just changing the orders in which we list these things, let's see how that changes the probability. So this is our new B, if you will. This is our new A. So the roles here have switched. This is now A, this is now my B. So the probability of this happening is going to equal the probability that it's a crime against society and it's motivated by religion. But now this is going to be divided by the probability that it was motivated by religion, not the probability that it was a crime against society like we had in our previous problem. Now, the tops of these things are the same. It's probability that the crime was against society and motivated by religion. Same thing happening here. So we're going to have that same probability on the top. We are still going to have that 12 divided by 5,351. The question is, what is the bottom going to be now? The probability that a crime was motivated by religion, okay, now we're just looking at all the crimes, the total number of crimes motivated by religion. Well, that was 1,092. So the bottom is going to be 1,092 divided by 5,351. And when you pull the same trick that we did in the previous problem, we multiply this fraction by the reciprocal of this one here, we're going to get 12 over 1,092. This is, if you simplify this out more, 1,092 divided by 4 is going to equal 273. So 12 over 1,092 is the same as 3 over 273. And you can actually break this down even more. This is equal to 1 over 91. So the probability that we had a crime against society, given that it was motivated by religion, is a different probability than the probability that we had a crime motivated by religion, given that it was a crime against society. So this nicely shows that the order in which you list these things here, when you're doing the conditional probability, the order does matter. 1 over 91 is slightly more than 1%. 3 over 11 is going to be just over 27%. So not the same probabilities there. So the order in which you have things listed in your conditional probability, it does matter. So guys, this concludes our video on multiplication rules for probability and conditional probability. If you have questions, be sure to reach out to me. Emails, texts, phone calls, banners flying on the backs of planes up in the air, sending carrier pigeons, whatever you have to do. Until the next video, take it easy, guys.